All right, so example 4b6, this can be found on page 224 in your dynamics textbook. The given states, the system shown below is made up of particles A, B, and E at 5 kilograms, 20 kilograms, and 80 kilograms respectively. Lightweight bars OB and OA are welded together such that there is a right angle between the two bars, and these bars are welded to the pulley at point O. Consider the mass of the pulley to be negligible and the system released from rest when theta is 0. So we are trying to find the speed of particle E when theta is 90. There's a couple more givens right here, but we won't be using those since we are going just to be solving this problem symbolically for the time being. And so this is what our diagram looks like for this problem as well. All right, we are going to start off with step 1, which is drawing your free body diagram. So our first step, so obviously there are 3 particles. We have E right here, B right here, and A. So we're going to be drawing the free body diagrams for BE first. So we're going to draw a box right here, make that just a little bigger. And then we are going to draw our forces that are acting on it. So weight is going to be the only one that's going to be acting on this because the problem did state that consider the mass of the pulley to be negligible. So that means we're not going to have any force tension right there. Then we're going to go in and draw B. It's a nice little circle. And again, we're going to have, let's see if I can draw this arrow. And then again, we're going to have weight B down. And then we're going to draw another particle, make that just a tiny bit smaller. And this is going to be our WA. So we have our free body diagram set up. Step 2 is going to be setting up our coordinate system. So right now we're just going to use a standard coordinate system. And we're going to use I and J. If this works, there we go. So we have I hat and J hat. All right, step 3. Which is going to be putting all of our forces that we drew in this free body diagrams for all 3. So it's going to be WE, WB, and WA. And we're going to put that into vector form. So we're going to just go WA, WB, and WE. So WA will be the mass of particle A times gravity, J hat, because it is going down. And that's also why it's negative. So we'll have negative mass of B times J hat. And then we'll do the same thing for E.
All right, for step 4, we are going to write out the acceleration equation for particles A, B, and E in vector form. So for particle A, we get the acceleration of A is equal to the acceleration of A in the I direction plus the acceleration of A in the J direction. For particle B, we get the acceleration of B is equal to the acceleration of B in the I direction plus the acceleration of B in the J direction. And for particle E, we get the acceleration of particle E is equal to negative AE in the J direction. For step 5, we are going to apply Newton's second law sum of all forces is equal to mass times acceleration. Now, since the only forces that we have for all three blocks is just mass, for block E, we are going to get negative mass of E times gravity, the J direction, is equal to mass in the E direction times negative acceleration of E in the J direction. And from this we get our two scalar equations for I and J. For I, it is equal just to 0 since there's no forces in the I direction. And for J, we get acceleration of E is equal to gravity G. For block B, we get negative mass of B times gravity in the J direction is equal to mass of B times the acceleration of B in the I direction plus acceleration of B in the J direction. And when we get our scalar equations for this, we get in the I direction, 0 is equal to mb times acceleration of B, since there's no forces in the I direction. And for J, we get the acceleration of B is equal to negative gravity. Then for block A, we get negative mass of A times gravity in the J direction is equal to mass of A times the acceleration of A in the I direction plus the acceleration of A in the J direction. And when we get our scalar multiple equations for this, we get 0 is equal to mass of A times the acceleration of A. And for J, we get the acceleration of block A is equal to negative.
All right, for step 6, we're gonna do kinetic energy for masses A, B, and C. So we're gonna make our little chart. It's important to acknowledge that the problem says it starts at rest. So at position 1, all of your kinetic energy, or all of your velocities, will be 0. And then for position 2, we will have the general kinetic energy equation, which is 1/2 mv squared for each of the individual masses. So for MA, it's going to be 1/2 MAVA squared. And you're going to do that for each one. All right, for step 7, we're going to make a chart for the potential energy. It's important to note that the only potential energy in this system is gravitational, so you're going to use the equation mgh. So make sure you write it all out for each mass A, mass B, and mass E. So for MA, the starting position is below the reference point. And so your V1 will be negative MAG, and the length of that rod is 2L, so that will be your height. And then for mass B and E, they're at 0 because they're at the 0 reference point. For V2 of mass A, that is moving to the 0 reference point, so that will be 0. Mass B is negative MB B, G, L, because the length of that rod is just L. And for ME at position 2, it's going to be negative MEG in the delta E, which we will explain later.
All right, so now we're going to move on to step 8, which is work done by non-conservative forces. And in this problem, there's no non-conservative forces such as friction. So our UNC from 1 to 2 is going to be equal to 0 joules. And to continue on with step 8, another important step in this problem that will help us when we get to our work energy equation in step 9 is kind of to define what delta E is as stated in the previous steps. So delta E in this case is the change in the height that the block E will move down when the system moves. And we're going to define this as R times theta. And since we have theta as 90 degrees in the problem statement, 90 degrees is the same thing as saying pi halves in radians. So we're going to write this as pi halves times R. Then we can also define our velocities in terms of theta and theta dots and the distance that they're going to move. So we have VE is going to be the change in theta, or the rate, so theta dot times our distance, which is R. And then we're going to have VB be equal to the rate of theta again, so theta dot times the distance that B is from our zero reference, so that would be L, and VA would be theta dot once again, and the distance that is from the zero reference is 2L. So then solving for all of these to plug back in to our work energy equation to get, so then we have just VE in the work energy equation. We're going to have to solve for theta dot right here. So it's going to be VE, messed up a little bit there. So we're going to have VE over R. And then we can solve symbolically in terms of, for VB and VA, when we plug in theta dot to each one of these to have all the terms in terms of VE. So VB would thus then be VE over R times L, and VA would be equal to VE over R times 2L. All right, to finish this problem up, we're going to get to step 9, which is the work energy equation. This equation is defined as T1 plus V1 plus UNC from 1 to 2 is equal to T2 plus V2. Being that our T's are kinetic energy and V is the potential energy and UNC is the work done by non-conservative forces. So we've already solved for most of these in previous steps, so we're going to plug them in and then solve symbolically for VE. So when you do this, we're going to have T1 would be equal to 0, V1 would be equal to MAG times 2L, and our work done by non-conservative forces, as we previously stated in step 8, was 0 since there is no forces. So that would also cancel out. And then for our kinetic energy at position 2, we're going to have 1/2 ME VE squared plus 1/2 MBVB squared plus 1/2 MAVA squared. And then for our potential energy at position 2, we're going to have minus mBg times L, and then minus MEG delta E. Being the delta E is our change in the height that E will move. Then to continue on with this step, we're going to solve symbolically for VE out of this whole equation. And just to save some time, we're going to skip right to the symbolic solution for this problem. And so VE would be equal to negative MAG times 2L minus MBG times L minus MEG pi R over 2 minus MBL squared over 2R squared minus MA4L squared all over 2R squared. And this whole mess is going to be all over ME over 2 plus MB over 2R squared plus the mass of A over 2R squared. And this entire equation that we have wrote down is all square rooted. And if you would like to continue this further, you could plug in